Right, so we are live. Okay, so today we are going to continue this journey of finding ranks of transformation semigroups. Okay, so what was our goal? Our goal was to look at the collection of all functions from finite set n to the same finite set n, and we wanted to find the minimum number of generators needed to generate that entire collection via composition, if composition is the operation. It's a very natural question. We answered that question. But then what we said is we are not satisfied with that. We want to ask the same question for special sub-semigroups of the semigroups of the semigroup of the entire set of transformation. Okay. Then we saw how to answer that question. We naturally, at least we have not seen it, but we have come to the idea of how we come down to simple semigroups, because we bring down the problem to that of J classes, right? We bring down the problem of finding ranks of the big semigroup to J classes, and J classes are simple because J class is simple because any two elements in the J class generates the same two-sided ideal. So J class will not, a J class when looked at as a semigroup will not have any proper ideals and so on. So we are naturally down to, first of all, finding ranks of J classes or finding ranks of simple semigroups, which are also completely simple semigroups, which mean that they have minimal J classes. They have minimal left and minimal L and R classes and such things. And so we have developed some theory for that. We have developed some structure theory for that and so on. And then we looked at the rank function. We gave a lower bound. So that I think was a little earlier, but yeah, we did give a lower bound to a semi. So first of all, any semi-group S, okay, if it's completely simple, then we know that it has a group part which is right in the corner, here, right? And then we have the number of rows and the number of columns, and then we saw that there was a matrix P which decides the multiplication, right? So that's um, that's very cool, I guess. And then we gave a lower bound to the number of generators. That is, it will be the max. It will be at least the max of, yeah, so the rank of S would be at least the max of the number of rows and number of columns. So this is something that we proved. Then we saw that, right. This was the case even when we went modulo the group part. Okay. Right. So we are naturally down to the case of those simple semigroups in which the group part is the identity. So that's what we look at today. So that's the material for today, is we want to look at those completely simple semigroups in which the group part is trivial. Okay, so the thing in the corner, if I may draw a picture, if you look at the semigroup, then the group H class in the corner is just the identity. So every group H class would just be one element, right? Every group H class, or every H class in fact, would just be one element. Okay, yeah, it would just be one element, some element H, and either that H will be invertible, in which case H square is going to be identity, or it may be nilpotent. Sorry, or it may be nilpotent, yeah, or H square might be H square might be 0. Right? So this is the characterization which we had seen, that in a completely simple semigroup, every H class is either null, meaning the square of it is 0, or its square is itself, and hence it's a group, in fact. But in this case, our H classes will be just made up of one elements, right? So if that is the situation, then we can very well just look at our semigroup as, in that case, we can very well just look at our semigroup as just indexed by the row and column numbers. Every cell is just this index because every cell has just one element. So it can very well just be indexed by I comma j, because the g that is there in here, or some g that is there, or um, yeah, do you need a g always? Yeah, but uh, in any case, I mean, we can just do this, right? We can just do I comma j. Um, right. So yeah. So I let me say, so it will be I. So in general, in general, it is I comma g comma j, right? But here there is no g. The g is element of the group of that corner of the group in the corner. But there's no. But here is just the identity. So that's just one. So we don't really need to mention it. Okay. So the point is in the end that you can look at the semi group. You can look at every H class as just because it's one element. You can just look at it as just call it I comma j. And then we can see what the multiplication breaks down to, simplifies to. So the idea is that so we know that I comma lambda and times j comma mu. So we know that in general, I mean, we know the rule says that in general, this, to be precise, we'll have to say this. Right? I mean, if we were to be precise, if we were not to abuse the notation, we would have to write it like this. But then that means that this would be I comma 1 times p of this, where p lambda j is the element in that matrix p, which will just be a 0 1 matrix, because in this case it is just there is this one element in the group, right? And then times 1 again, and then comma mu, right? So, well, what do you know? I mean, this will either be 1, this will be 1 if and only if p lambda j. So this is wrong here. It is j. Just my own way to write. So that will be 1, in which case we can just identify this with I comma mu. We don't need to mention the 1, or it will be 0, right? So the multiplication is very straightforward, right? The multiplication is very straightforward. You look at the matrix, and if p lambda I matrix is if element is 0 in the matrix, then it's 0. Otherwise, it's I comma mu. So let's just see it. So this is the semi group. It is not the matrix. So it is. Let's just see it. So if we have the I here, and if we have the j here, and let's say we have the lambda somewhere here and the mu somewhere here, and then if you look at I comma lambda, it is this, and then you look at this. So this multiplying these two is sort of just taking that vertex of the rectangle. It is just taking, so the product of these two blue dots will just be this black dot. It will either be the black dot. Okay, it will be the black dot if p of lambda I. Okay, so p of lambda I is not here. P of lambda I is a different matrix. Okay, that's it to look at. Okay, if p of lambda I is 1, then it is this. Otherwise, the product is 0. Okay, so this is the rule that we know that was present in the multiplication, right? So yeah, so this is very simple. So the point is that the multiplication is very simple. Okay, yeah, it is very more than simple. I must say it's very combinatorial. Okay, so 1 second, something is wrong. I have to, oh, 1 second. Minute. Yeah, I'll just fix it. 1 second. I pressed some wrong buttons, and yeah, right. So we understand the object that we are looking at. Okay, and before finding, now we want to find the rank of such a semigroup. Okay. Now, as we already understand, this multiplication depends heavily on the matrix P. Okay, and if you think about it, this matrix P in some sense just decides the multiplication. That is just decides the multiplication. Of course, the indices are there. Along with the indices, the matrix P is the key. Yeah. Now, we can find the rank of these things. Okay, to find the rank of these things, we would want to first understand when two such things, when two such semigroups are isomorphic. Okay, so we have the semigroup S1, where again you can take the G or you can just call the G identity, but to understand when S1 and S2 are isomorphic, the group part can be trivial and can be non-trivial. It's not very important. Okay, as long as the group is same for both. But obviously, we just need to know this result for G being the identity, and maybe that's a good place to start because that's not the important point here. So you can assume that G is just the identity. Okay. Let's say you assume that, then you have these two semigroups in which these indices, the number of rows, number of columns is same. You can notice this, right? And this is obviously the first constraint. If that is different, then they have different number of elements, and so there's no way they can be isomorphic. So that's obviously the same. But the matrices P and Q are potentially different. And the question that we are asking is, when are they isomorphic? Okay. Because obviously isomorphic semigroups will have the same rank. Okay, so if you can say that P is isomorphic to some simple version of it, some maybe identity or some the simplest. So basically in the isomorphic class, you would want to look at the simplest member where P is the simplest, and then you can find the rank there. So it's good to understand what the isomorphic classes are like, and it's not very difficult to see what we'll see. So um, right, and so we will see what that will do to it. Okay, so when are they isomorphic? Let's see. So let's say, so we take the Q different in this case, but it's not very different in the sense that you look at this, we have the matrix P, but then the Q is just P, but only the first and the second columns are swapped. Okay, so P and Q are the same, except that the first and the second columns are swapped. Okay, what does it mean? It's what I said, but it just means that sorry, it just means that if you're looking at the first column, this would be equal to Q of swapped, it would be Q of lambda 2. So just the columns are swapped, right? That's what this means. And the claim is then that these two semigroups will be isomorphic. Okay. And how do you show that? So, well, I mean, if you have this 1 comma g comma lambda, okay, which is, so this is the first row, and this is the lambda-th column, okay, and there's a corresponding group element. What does, so this is in P, in S1, what should this correspond to in S2? Okay. Now, if you think about it, this P of lambda comma 1, right, this P of lambda comma 1 controls the multiplication, right? It controls the multiplication, and it looks at the first. So yeah, okay, let's not do it like that. If you just send this 1 to 2, okay, so remember here you are swapping the columns, okay, but here I'm just swapping the rows. Okay? I'm sending the element which is sort of in the first row to the second row, and similarly elements of this kind which are in the second row, I'm sending them to the first row, and let's see how this works out. Okay, so now if you have two elements I comma g comma lambda and 2 comma h comma mu, then if you multiply them in P first, then it will become this. Now note here that if you're multiplying them in P, is becoming this, and this is P lambda comma 2. Now see, P lambda comma 2 is in the second column, right? But it is really deciding the multiplication of what something that is in the second row, right? is deciding the multiplication of something which is in the second row. And if p lambda comma 2 is q lambda comma 1, then I must send this 2 to 1. I must send this 2. I must send the 2 in the row to 1 to the first row. And that was the motivation behind swapping this row. So if you just write this multiplication out in P and you want to see what this becomes in Q, then you can, if you just relabel this by Q lambda comma 1, then you will know what to do. Right? Q lambda comma 1 means that this should have been become 1. But let's just do it formally and check. So if this were to be equal to this, which is the definition of isomorphism, then this phi of I comma g comma lambda will remain the same, assuming that I is not equal to 1 or 2. Okay, but this 2 becomes 1. Now, because this 2 becomes 1, you see this becomes q lambda 1, right? But then we know that this q lambda 1 is p lambda 2. This q lambda 1 we know we know that this is p lambda 2, and so we get p lambda 2. And yeah, so just give me 1 second. I mean, if you don't want to say p lambda 2, then just say q lambda 1. And this we know by the isomorphism that this just becomes this. It just remains the same because this is I. And then we know that this p lambda 2 is equal to q lambda 1, right? So they are equal. So these two are equal. Okay. So the idea is that, I mean, this the what happens to the columns of the P or the Q matrix. The same thing happens to the rows. That affects the rows of your original semigroup. Okay. That's why when the columns are swapped there, then the rows are swapped here. And the rest is just simple checks. Okay. So what we have done is in fact something significant. Okay, it's a small step, but again, it's sort of we are again using that the fact that this permutation group is generated with swaps, right? Swaps, and yeah. So we understand that, I mean, if Q is gotten from P via swaps of rows or columns. I mean, swaps of columns here, which what we have shown, or rows. 1 and the 2 is not special here. This column is not special here. You can do this for rows and you can do this for any 2 rows and any 2 columns. So if Q is gotten by any number of finite number of swaps, Pn of the matrix P, then Q, the S2 would be isomorphic. Okay, S2 would be isomorphic. That's right. And so instead of working with the matrix P, we can just swap the rows and we can simplify the matrix and so on if we want to, right? So that's how we will use this. Okay. I mean, yeah, so it means that if you get Q by permutation of rows and columns, then there will be P and Q. If you get Q by permutation of rows and columns of P, then S1 and S2 will be isomorphic. Okay. Right, because any permutation you can get by transpositions. But the converse is also true, but I do not think we need it. Yeah, you can do the same thing. The converse is also true, meaning that if they are isomorphic, then the matrix Q is made up of swaps, is gotten from a permutation of P and Q. Okay. Now this is not needed for us, but if you really think about this, I mean, if you really think about this, if S1 is isomorphic to S2, right? If S1 is isomorphic to S2, okay, and let's say phi is an isomorphism, right? Then phi will permute the first coordinate and the last coordinate. What does it mean? It means that, let's look at example. You take the first coordinates, right? You take, and you take two, so you keep these to be the same and so on, right? And then if you apply phi to this, right, then this would just get permuted, right? I mean, the first coordinates will just permute in the sense that if I comma g comma mu uh, phi of that cannot be equal to phi of j comma g comma mu. I mean, two different rows cannot be collapsed. Otherwise, the size of the L class. So I mean, if they collapse, then it's not this. Then it's not. Uh, so the way to think about this is if there are two rows I and j which are different, right? And you are collapsing them in your image matrix. So then the number of R classes will not be the same, and then it doesn't really work out. Then they're certainly not isomorphic. So yeah, with those things, we understand that the row, it will just be permuting the first and the last column. Then you can use those permutations to actually decide on how you need to permute the p and the q, how you need to permute the columns and rows of p to get q. So from this we can build the permutation matrices and so on. So, but we will not need that. We will not need that in the sense that we will just work with the simplest member in the isomorphic class. Okay, which we would just use that it's gotten by permutation. So we know that it is isomorphic to S1. Okay, we'll be working with that kind of S2, and we will know that it is certainly isomorphic. We will not be assuming that it's isomorphic and saying something that this has to be permutation and so on. We'll not be using that direction, so we don't really need it. So yeah, that was the first step, was to simplify. And we'll see its implications right now. Let's see its implication right away. Okay, so how we can do this is, okay, so um, 1 second. Yeah, so before we actually start calculating the ranks of semigroups, like of completely simple semigroups in which p is special. For example, we'll take p to be the identity matrix and so on, and we'll try to calculate. But and obviously g will be identity in our case. Okay, that's will always be the case. Okay, so before we do that, we have made the simplification, but at the same time, we will use a simple combinatorial tool. Okay, which we will just see right now. So again, just to make the context clear, the semigroup we are working with, the group part is trivial. The group part is trivial, so it's completely combinatorial. The multiplication is combinatorial. You've seen it, and this is what it is. Okay. Let us see this sort of a recursive lemma. So what is it about? It's about reduction of calculation of the rank of a semigroup of this type to a smaller semigroup. Okay, that's what we're doing. So let P be a regular n cross m matrix. Okay, of obviously over zeros and ones, because our uh, group part is trivial, and it's a regular because we have seen this, that for completely simple semigroups, the P has to be regular in the sense that every row and every column must have at least one zero. Sorry, at least one, at least one group element. So in this case, at least one. Okay, that is um, that is our base assumption, right? That is the assumption that's based on the fact that every row and every column must have a group H class in a completely simple semigroup. So yeah, but let's see the lemma. Okay, so let's say that M is more than N, so you have more. So this is the N cross M matrix. Okay, that is because semigroup is sort of M cross N. The I is M, and the wedge, what do you call this? The wedge is N. Okay, so P will be N cross M, right? We have seen this because the row and the column. Anyways, yeah. So we have seen this. Now, if M is bigger than N, right? So if we have more columns than rows, okay, then the idea is that you can remove a column, right? You can remove a column, you can get rid of a column, and still keep this regular. Okay, that is the key. Whenever you have more columns, you can remove a column and you can still keep it regular. So you can get rid of some extra. So the idea is that there's a column which is redundant. How are we going to do this? So obviously, we have to maintain the regularity. So to maintain the regularity, we'll traverse the rows. Okay, we are, let's say, in the first row. We are in the first row, and we pick the one. We pick the group element, in this case 1. We pick the one somewhere. We don't know where it is, but it will be somewhere it will be there. Then we come to the second row and we pick a 1 there. Now it fits the same column, that's good, but we don't need to assume that. I mean, that's better, but it can be, in the sense that if it is in the same column, it's only better for us. We'll be using lesser number of columns. But in any case, you can traverse and you can find 1, 1 in every row because it's a regular matrix, and so on. Now, by the time you reach the nth row, you would have used at most n columns. And so there will be some column which you don't use. And you can really get rid of that column because the rest of the columns would still have ones, because columns having ones don't depend on other columns. And the rows having ones, we have already taken care of it. And so this will still be regular. This is interesting lemma which will be sort of used in induction in an inductive manner. And it's such a simple lemma. Right. So let's keep rolling. In the same way, if you have more rows, then also you can remove a row. But the third one is interesting. So if you have, so if n and m are equal, so if it's a square matrix that you're looking at, and if p, so this means that this notation just means that P can be gotten from the identity matrix by permutation of rows and columns. Okay, permuting rows and columns of P gives you the identity matrix. Why are we interested in this concept? Because we know that if you have a matrix P, which you can, whose rows and columns you can permute to get the identity matrix, then the semigroup corresponding to this matrix P would be the same as the semigroup corresponding to the identity matrix, right? They will be isomorphic. That's what we have shown, right? That if S1 and so if P1 and P2 are, no, 1 second, right? Yeah, if, so we are not using the isomorphism, yeah? So once again, we know that P is gotten from the identity through permutations, so the semigroups corresponding to them will be isomorphic. This is what we explicitly showed. So that's why we are interested in this concept, whether it is similar to the identity matrix or not. Now, what does it mean? I mean, if it is similar to the identity matrix, then obviously every row of P must have a 1, right? And every column of P must have a 1. Otherwise, there's no way in which you can permute the rows and columns to get the identity matrix, right? Because if you have a, so let's see, if you, let's say, have a row in which the one here, there's a 1 here. Now this, you can permute the rows or you can permute the columns. You will still have 2 1s in this row or wherever this row goes. Okay. And if you permute the columns and the row is the number of 1s in the row is unaffected, right? So certainly this will never be the identity matrix. On the other hand, if every row and every column has a 1, right? If every row and every column has exactly a 1, exactly 1 1, okay. Then certainly it is equivalent to the identity matrix, right? You can just do that, right? You can just, so if every row and every column has a 1, then the first column will have a 1. So here it is here, and let's say, for example, if this is here and there's a 1 here, then you would bring this row to the second row and so on, and you can get the identity matrix through this. Okay, if every row and every column has a 1. So every row and every column having a 1 is the same as it being equivalent to the identity matrix. And it is also, it's very clear that now you cannot afford to remove any row or column, right? Because everything is just fits uniquely. And so obviously you cannot, I mean, if you remove a row, then it means that you have removed a 1 which was only there in this, which was the only one in this column. If you have removed this row, so this was the only one in this column, and so if you remove this row, then this column will not have a 1. And so all of it just hinges on the fact that every row and every column has only 1 1. And in that case, you cannot remove. So this is a situation in which we cannot reduce. So it will be important for us to do this case without induction. We'll have to do this explicitly, but since it's But since we have proved the isomorphism result that such a matrix would be just same as the identity matrix, isomorph up to isomorphism and so up to generators, number of generators. So we will not even have to worry about it too much. We will be able to find it because the multiplication corresponding to the identity matrix is what we just then will need to look at, and that multiplication is quite simple. So we'll see. Yeah. So I think the combinatorial lemmas are through there, but let's just have a look at them again. There is another lemma which is there. Okay, such matrices are, so this is a point I was making. Such matrices are irreducible in the sense that we cannot remove, delete things and reduce it. So we will have to do them explicitly, right? And we can do it because we can reduce it to the identity matrix. Just I was just saying. Yeah. Now there is another kind of reduction. So this is probably the last thing we'll do. So we'll be done with our lemmas, and then next time we can actually prove stuff about the identity, about semigroups in which the group part is identity, and then we'll prove it about semigroups in which the group part is not identity, because the semigroups we'll be looking at, this subsemigroups of the transformation semigroup, the group part will not be identity. Okay, but it will be what is known as idempotent generated, and we'll prove some interesting results there. Okay. But anyways, now if n is equal to m, if n is equal to m, and p is not equivalent to the identity matrix, then that means that there is a row with two ones. But because the row and the column number is same, you can check that there is a column with at least two ones. So you can just remove that row and that column by point number 1 and 2. Right? And we can just take an example. I guess it will be more clear. So let's take a 4 by 4. I mean, it's amazing how very simple lemmas, this will go a long way. This will go a long way in showing that the rank is exactly equal to the lower bound. That is, it will be exactly equal to, it will be exactly equal to the maximum of the number of rows and columns, which is interesting. Which is like saying that removing the group part was the right thing to do, in the sense that when you remove the group part, then it's completely combinatorial and the rank is exactly the bound that we had got earlier. Okay, and then we'll see how adding the group part can change the rank, and that will really be the challenge, and it will be nuanced. It will depend on what kind of group part it is and side important generator or not, and so on. But anyways, this is finish off with this, and we can think about this. So if this is the case, and if we have two ones, if you have two ones in this row, let's say this is the only one row in which you have two ones. Okay, now you want a one in the second column, so you put it here. You want a one in the fourth column, so let's say you put it here. But then you want a one in the last row as well. So you have a row which has two ones. Now you want a one in the last row as well. So this will force you to have a column with two ones, because you have more number of ones and number of rows, and hence more number of ones and number of columns, and so you will end up, wherever you put, you will have a column with two ones. Okay, now because you have a column with two ones, okay, if you traverse, let's say here, so you found a one in the first row, let's say this, then you go to the second row, you have found a one here, you go to the third row, you have found a one here, right? So you have found your ones. Now how about now if I remove, yeah, that's the problem. If I remove this column, then let's see if our matrix is still regular, right? And the answer is yes, right? If you, oh, hold on, no, I've made a mistake. So you cannot, 1 second. So if you remove this column, then it is not regular. So I don't know why I removed that column. I should have removed the other column. Yeah, but anyways, the point is that let's work it out again. That's important. Yeah, let's try to concretely, just give me 1 second, I have to just shift this side. Yeah, let's try to understand which column can we remove? Or let's say which row we can remove. Let's maybe think about that. So yeah, so certainly we can remove the last row, right? We can remove the last row. Every row has a 1, every column has a 1. This is what was the first, this is what was the second point. If we have more rows, then you can remove a row. Now you have more columns, so you can remove a column. I mean, it follows from 1 and 2, but we still try to just work it out. Now you can remove a column, right? Which column can you remove? I mean, you can obviously remove the last column. No, you should not remove the last column because this one is essential for the row. You can remove this column. Yeah. Now it makes sense, right? Now if you look at, so now if you look at it, it will be a 2 by 2 matrix. It will be this, this, and in fact, just the identity matrix. And it is regular, obviously, it's just identity. So it is, the point is that not just you can remove a row and it will be regular, you can remove a column, it will be regular. No, but you can remove a row and you can remove a column such that it's still regular. Right? So you can do both in the same, you can do them in succession and still have a regular matrix. So this will really help you in reducing the case in which n is equal to m and p is not similar to the identity matrix, meaning that it has more than one in a row and in one column. So it's really a very nice balance, right? Because when the matrix P is simple, meaning it's equivalent to the identity matrix and you can't reduce, but then the multiplication is simple, so you can do it directly. And in the case it is not equivalent to the identity matrix, then the multiplication is more difficult, but then you can reduce. So it's a wonderful way in which this fits. Right? So I think it's a good way to end. So it's a combination of explicit enumeration. Okay, and in the case of P is equivalent to the identity matrix, this is even an interesting question because this way in which you can enumerate and the number of such bases in ranks and number of different generators, number of bases is a good problem to do and things like that, which we'll see later. But for the time, we'll just prove that the lower bound, the obvious lower bound is equality. So that's what we'll prove. Okay, that is not today, but okay. So this is when it's equivalent to the identity matrix. Then we'll go to the case in which it is not equivalent to the identity. But yeah, that is to come. Meanwhile, maybe you people can try to, I mean, you can just try to think about yourself how you can use this inductively to show maybe a quick glimpse to show this, that if the group part is identity, I mean the problem is combinatorial, and P is a regular m by n matrix, and the rank is the maximum of the number of rows and columns. It's a remarkable result. This is the first step. We'll see the proof of this. It's simple. We'll see it the next time. And I think this is a good place to stop this. Yeah. Thank you.